We're going to develop the formula for arc length, not arc length as in s equals r theta that we may have first seen in trigonometry. This is a different formula. And we can approximate the length of part of a curve, that's what's meant by arc length here, f, by summing distances between points on the curve. Here's a little diagram here. Suppose this is our curve, and we have, let's say, 2 points on the curve, and we're looking for the distance along the curve between the 2 points. We can approximate that by taking the linear distance between the 2 points, but that was going to be a poor approximation. We can increase the accuracy of our approximation by increasing the number of points that we're considering. And between any two of these points on the curve, there's a distance. And what we're eventually going to do is let the number of points on the curve go to infinity, as you may have expected in calculus here. We can represent the distance between 2 points on the curve as di. So for this image here, suppose we have here 2 points, f of x sub I minus 1 and x sub I minus 1 f of x sub I. The distance between those 2 points is what we're calling here d sub I. D sub I can be expressed using our distance between 2 points formula. So d sub I is the difference in the x coordinates quantity squared plus the difference in the y coordinates quantity squared, all inside of a square root. And we can express that as delta x sub I squared plus delta y sub I squared, all inside of a square root. By multiplying and dividing by delta x sub I, but we have to be careful when we do that. I'll finish that thought in a minute, because what I want to do is eventually I want to keep the delta x sub I in the numerator outside of the square root, but for the delta x sub I in the denominator, I want that to go into the square root. They essentially have to be the same language the square roots do. So I'm going to multiply in the numerator by delta x sub I, in the denominator delta x sub I squared square rooted. Doing that, I can express d sub I as the square root of 1 plus delta y sub I over delta x sub I, the quantity squared, times delta x sub I outside of the square root. This is starting to look like something that we can put into an integral, but first we're going to reference the mean value theorem. By the mean value theorem, if f is continuous on a closed interval from x sub I minus 1 to x sub I, and differentiable on the open interval from x sub I minus 1 to x sub I, then there exists an x sub I star such that that x sub I star is between x sub I minus 1 and x sub I, so something inside of that I subinterval, such that f prime of x sub I star is equal to delta y sub I divided by delta x sub I. Using that fact, and then letting all of the delta x sub i's be represented as the same length, we can write down that d sub I is equal to the square root of 1 plus f prime of x sub I star squared times delta x. Then the length of the curve is approximated by L, is approximately the sum as I goes from 1 to n d sub I, which is the sum as I goes from 1 to n of the square root of 1 plus f prime of x sub I star squared times delta x. The length itself is actually the limit as n approaches infinity of that sum as I goes from 1 to n of the square root of 1 plus f prime of x sub I star squared delta x. This is, of course, an integral, and so the length of a curve as x goes from a to b is the integral from a to b of the square root of 1 plus f prime of x squared dx. And so the process to find the length of a curve from A to B, that's x going from A to B, will be to take a derivative, square it, add 1, put it into a square root, and then hope that we can integrate the result.